All right, good morning, everyone. It's 10 o'clock, so we will go ahead and get started. Welcome to the 2023 CRB Webinar Series. Today's webinar will discuss California's water availability and crop water efficiency strategies. My name is Caitlin Stanton. I'm your moderator today with the Citrus Research Board, and I'm joined by McCall Machado and Dr. Melinda Klein, who will assist with questions. We encourage you to ask questions throughout the webinar using the Q&A function, which can be found at the bottom of your screen. All questions will be answered following the presentation. So it is a pleasure today to introduce today's speaker. Please welcome VP of Design for Laurel Ag and Water, Dr. Franklin Gaudi. In his role, he works to elevate irrigation industry standards by training account managers and engineers in all facets of irrigation design and management practices. Before his current role, Dr. Gaudi was an assistant professor and a project manager for the Irrigation Training and Research Center at Cal Poly State University's Bioresource and Agricultural Engineering Department. He taught courses in irrigation water management, on-farm irrigation systems, fertigation, landscape irrigation, and AutoCAD. He also taught many of the irrigation short courses through the ITRC. He served as a member of the Irrigation Association Certification Board, where he helped maintain certifications and develop new ones. Dr. Gaudi is also recognized through the American Society of Agronomy as a certified crop advisor. Dr. Gaudi, I'll put your presentation up on the screen and then we can begin.
Very good. All right. Well, welcome everybody. Thanks for joining us. I'm gonna hopefully give you guys some new information that you haven't maybe had or seen yet this year. Obviously, everybody knows that we had a pretty good year in terms of rainfall and so forth. So I want to cover that a little bit, and then I also want to kind of go through, some strategies that you might consider on farm, in your citrus orchards. So feel free to ask questions, via the chat, and I think Caitlin and McCall will help, make sure I get those questions answered. So here we go. So I believe I have access here. Yep. So the first thing I want to start with is background on California water availability, kind of just give you a little bit of overview of, where we've been, where we're at currently, and discuss a little bit about that. So just to give you a little bit of an idea here, obviously that's the earth. This particular area here is all of the water on earth. So anyways, there's a little tiny dot there on the right. So you see earth, you see the big blue dot, and then there's a little tiny dot right there. And that particular dot, it represents all of the fresh water that's actually on earth. So right there. All right. So if you were kind of to look at, compared to earth, we've got a little tiny amount of water on earth. And in fact, it's about 2% of all of the water on earth is actually fresh water, something that we could potentially use or have access to. So looking at it here, you've got the option here for right there is 2.5%. So if you break that down into this here, that's our 2.5% of all the water on earth, but around 69% of it is tied up in as ice. And then another 30% of it here is groundwater. So that leaves not a whole lot of, water here that's actually on the surface that we can use as fresh water. And then when you break that down even further, a lot of that actually is tied up as groundwater ice. So so you look at it, you start breaking that down 2.5%, and then only 1.5 or 1.2% of that is actually fresh water. And then of that 70% or so, 69% is tied up. There's not a whole lot of water, to use. And so that's really our problem that we're seeing is that there's the same amount of water on earth today as there was a million years ago. The problem is that water is just in different locations, depending on, cycles, weather patterns, and so forth. And so, some years are good, other years aren't as good. And the bottom line is that there's not a whole lot of fresh water, and that fresh water that we do have, a lot of it's tied up as ice. So keep that in mind whenever, we say we're in droughts. It's not necessarily that we're in that the world is in a drought. It's just that the location that we're in is in a drought. So we had a pretty good water year, but you go to other parts of the United States or even other parts of the world and they're in a drought because that water is just in a different place at a different time. Kind of to go through that a little bit, you'll notice here on the next slide, this is snowpack over the last 10 years or so is something I'm going to show you. And just to give you an idea, 2013 was a pretty good year. 2017 was actually a record-breaking year in terms of the amount of rainfall that we got. This year, 23, and I'll show you, was actually a record tying, I would say, year for snowfall. And so I want to kind of just go through this, kind of give you an idea of where we're at, what we've got. So you can see over the years there, you have dry years, 12, 14, 15 were pretty dry. 13 was okay. 16 was the 16/17 year. This is, by the way, on the January 1st, basically, or actually the 16th here, January 16th of each year. Also in January of 18 and 19, you can see 18 wasn't that great. 19 was, again, another good water year. You can kind of see a pattern there a little bit, right? Like every 4 to 7 years or something like that is typically when we will get a really good water year. And then you have your years in between that aren't as good, obviously. So, you've got 20 and 21 as well. You can see 20 wasn't very good. 21 also wasn't very good in terms of snowpack. We're, well below average for those years as well. So 13 was pretty decent. 17 was record breaking in terms of rainfall. 19 was pretty decent. And then, now we jump across to 23 and we have another good water year again. Just give you a couple pictures, right? 2019 again was good. This is Lake Oroville. It was full. By 2021, it's empty, so not quite empty, but close to empty, right? Close enough that people are concerned that there's not enough water. So, we get maybe 2-3 years worth of storage here out of our reservoirs, and we're needing water again. And that's really the crux of our problem here, is that we might go 4, 5, 6 years of drought, meaning, less than average water years, and the reservoirs aren't quite big enough to get us to the next big water year. So, then we start looking at water conservation measures and so forth. All right, so here's 22. Again, January of 22 wasn't super, by any stretch of the imagination, especially when you compare it to 23 here, which I'll show you 23 now. You can see in October of 22, everything is, of course, there's no snow up in the mountains, but you look there at March of 23 and you can see a huge, that's a substantial amount of snow. In fact, it was record setting snow, right? And so I want to kind of show you just a few graphics too that kind of highlight how much snow that was. So this is, year over year here for the last, I guess, 20 years there. You can see how much snowfall we've had. And on April 1st, we were well over 300% in certain regions. This is the average of the entire Sierra Nevada mountain range. But you can see we were like 300% of average in April, which is substantial, right? That's a lot of snow. In fact, you guys have probably heard about, some flooding in certain areas, and reservoirs are now full. And so I'll show you a little bit of that too. This was a graphic that I found that I thought was quite fascinating. This is on May 31st. So, today's almost the end of June here. So about a month ago, we had enough snow at the end of May that it was equivalent to what we would have in terms of snow on April 1st of an average year. So we made it an entire month past, or actually 2 months, right, from April, because it was April 1st through May 31st. We still had as much snow as we typically would have on April 1st, which is significant, right? And you can see we're 300+% of average for May 31st. normally we're down to a couple inches left in May 31st, and you can see we still have 20 inches there available in snow. So, and that snow now, of course, is starting to melt and starting to make its way down into the valley floor. All right. So I just wanted to show you this too, because I was all about snowfall. This is actually about precipitation here. In this particular case, you can see that the current amount of rainfall actually is not record setting, right? You can see there that it's, it's actually over the last 30 or 40 years here, it's only actually the 4th highest amount of rainfall. So what that means is that this particular storm was very cold. And that's part of the reason why I believe too that, we haven't seen like real hot weather yet this year either. It was a cooler season. So therefore we got more snow. And now that you have all of this snow up in the mountains, I believe it's almost acting kind of like a, to help keep the temperatures more mild, because you have a lot of energy up there in terms of ice that's slowly melting, and potentially that's part of the reason why we're seeing less not as warm temperatures here. So this is, by the way, this is the northern region. You can see on that little map to the top left up there that this is kind of in the northern Sacramento Valley. We got about 64 inches or so far. Compare that to 17 and 19, right? We still didn't even actually get as much rainfall as we got then, but we got a lot more snowfall. So this is kind of the central region here, North San Joaquin Valley, I'll call it. You can see that, again, we're still at about 63 inches of rainfall there. And again, still not record setting in terms of rainfall, but quite a bit better than we would typically get at about 40 inches. And then the next one here is the kind of the lower region, which is, southern San Joaquin Valley. And you can see there that we got 51 inches of rain. So that one's a little bit closer to matching some of the records in terms of precipitation, but still not enough to quite get us there. So again, lots of snowfall this particular year, but actually not as much rainfall as you may have thought based on records here. So all right, so this is kind of an interesting graphic here. This is the GRACE program, which is a NASA-based program. They use satellite imaging to kind of make estimates of water gains. They somehow are able to look at groundwater depletion and total water that kind of falls into regions. That yellow region there that's outlined is actually the entire delta. So if water falls within that yellow circle there, it will make it to the delta. And so we got a huge watershed there that will flow into the delta. So just to kind of put this in perspective here, the San Joaquin Valley flows, to the north, and the Sacramento Valley flows to the south, and they end up in the delta at the same location there. Okay, so the delta has kind of been a big deal. You guys are probably very familiar with the delta, and some of the issues that we have in the delta, the ecosystem there. It's some would argue that it is a sensitive location. We have the delta smelt, which is a small fish that is one of the native species of the delta, it's been in decline for years and years, and that particular fish is considered to be an indication or an indicator species. So since it's in decline, people believe that the delta is in decline. I'm not here to argue whether it is or isn't. I'm just stating what some of the facts that are out there about how people are looking at it. But because of that, because of channels, without as much vegetation, there's not as much habitat for the fish and so forth. The delta becomes a very hot topic, largely because of the surface area to the delta, right? And so then we pump out of the delta into the California aqueduct as one example. And so then we bring the water back down to the south along the west side of the San Joaquin Valley. And so pumping regulations are all set and everything based on, the conditions that we have in terms of how much water is available and how the, environmental health of the Delta is doing and so forth. So again, big deal. Well, according to NASA here, they have determined that if you were to look at the San Joaquin Valley area, so if you were to, you see that line that kind of goes through, the yellow line that kind of goes through that loop there, that's the San Joaquin valleys to the south. They were saying that we had enough rainfall that that entire basin there, if you were able to fill it up like a bathtub, that entire basin would have gained 20 inches of water. So, I mean, if you think about the number of acres that is in there, I don't know off the top of my head exactly what the number is, but it's probably in the neighborhood of around, 4 to 5 million acres there, all raising approximately 2 feet, right? Because 20 inches is almost 2 feet. So you can think about it as being, say 5 million times 2 feet, that's 10 million acre feet of water that was added just to that basin alone, it through the storms over the last, this last wet season. So pretty substantial. And you can see there the drought monitor basically is really kind of cooled off, going from that deep red color to maybe a shade of pink there. So it was a really good water year. We're hoping, I don't know if you guys have been paying attention, but the equator along the ocean temperatures along the equator, specifically up against Peru, are about 5 to 7 degrees warmer than usual. And that typically means that there's going to be an El Nino year. El Nino does not always translate into a wet year for California, but it does on, a fair amount of the time. And so with all of that record snowfall that we got, the rainfall that we got, and now potentially with a El Nino following this next fall and winter, we could find ourselves, really doing a lot more groundwater recharge, which is happening in a lot of areas, and really kind of reversing some of the conditions that we got to because of the drought. So things are really looking positive. Let's see if I can make this move again. I had the opportunity to fly over the Tulare Lake Basin, and so this is the Tulare Lake Basin, and there's probably about, I don't know the exact number, but it's over 100,000 acres now that is underwater, and it's because this water had nowhere else to go. The rivers are flowing out of the mountains, and we can divert as much as we can to do groundwater recharge, but this is the bottom of the bowl, so to speak, the bottom of the valley. And so water is naturally flowing into this valley. I think the last time they said it actually had water in it was 1983. So it's been exactly 30 years that this portion of the valley has seen water. So it's only about 1.5 to 2 foot deep at some of the deepest spots. And, it's taken quite a bit of production, ag land out of production this particular year. And projections are that this may remain for upwards of a couple of years, especially if we get another El Nino pattern, that this land will remain out of production as it, because this is very fine clay soils. It doesn't infiltrate into the ground very easily. And so, this has been a headache for certain growers. And then it kind of gets political too, because, there are berms out there and stuff to keep water from moving different directions, but it's getting close to certain towns. And so these towns have been, asking for them to be able to break levees to get the water out. And so there's a big political thing that I don't want to get into here, but it is a problem that, people are having right now. So luckily, things got underwater, right? And there's electrical service out there that they had to get airboats actually to go out there and disconnect electrical service and make sure that the water doesn't become energized and all kinds of stuff like that. But luckily, aside from a few homes and some shops and stuff that are out there, none of the towns nearby that I'm aware of have been impacted drastically. So doing a pretty good job of kind of managing all this water that we've gotten. All right, so just looking here at some reservoir data. This was kind of see up here. This is September of 25 there, and then over here is basically June 25th. So I pulled this in a couple days ago, I guess, and just so you can get an idea of how much the reservoirs have filled. So you can see we got the historical average there, which is the green line that goes across these. The blue bar obviously is how full the reservoir is, and the yellow is kind of the capacity of those particular reservoirs. So we have three really main reservoirs: Trinity, Shasta, and Oroville, that do a majority, in the Northern California, that do a majority of the water holding, for us. And you can see all three of those were getting to the point where people start to get nervous, right? And amazing what one good water year will do. You can see, aside from Trinity there, I'm looking at the chart on the right, aside from Trinity and Sonoma, pretty much all of the reservoirs, in the Millerton, of course, too, and that's probably an intentional keeping it low because they know there's going to be quite a bit of snow that's still melting. And so that's probably intentionally low to capture runoff as it starts to melt, to protect some towns and so forth. But Trinity and Sonoma, since they're on the west side of the state of California, a lot of those storms kind of just went right over top of them and fell on the Sierra Nevada range there. So we didn't quite refill Trinity, but there's no doubt that as we get some more rainfall in the north this next water season, that very well may make it all the way up to the top as well. So lots of positives here. And it's amazing what one, good water year will do. But again, unfortunately, these reservoirs only give us, 3 years maybe worth of water for our normal operations, between what is needed for municipalities, the environmental uses, and the ag uses. Good signs. All right, and so Lake Oroville, again, I kind of showed you a picture of Lake Oroville earlier. It went back down again in 22 and then right back up in 23 after a pretty good water year. So we're looking good. Looks like maybe I got a question down here, Caitlin, is it known roughly about how much groundwater recharge? Okay, sure. In terms of groundwater recharge, there are several irrigation districts that have Fresno Irrigation District is a really good example. They've been preparing for years for this kind of stuff, and they keep continuing to build out areas because their district has been kind of swallowed, so to speak, by the city, and so they provide flexibility to their growers by doing groundwater recharge basically every year, and then letting their growers that are in different areas pump out of the ground. So it provides flexibility because they have access to water whenever they want it. And so Fresno was very proactive in practicing groundwater recharge. And then there's the Kern Water Bank, which is going really heavy right now. There's areas in Bakersfield that are going, and I know we've worked on a couple projects with Laurel that we've helped growers get pumps and so forth in, so they can turn areas of their ground into recharge basins. If I had to guess, and I am 100% guessing here, there's probably in the neighborhood of 250 to 300,000 acres, I should say, that are currently sucking up water and putting it into the ground. And again, it's spread all up and down the state, and it very well could be a lot more than that. I obviously don't. I travel around and I see a lot of things, but I don't keep track exactly of the numbers. But just knowing in certain areas how much land we have, it's probably that. And in a lot of cases, those areas are sandy, and so they can absorb in the neighborhood of about a quarter of a foot per day, so we can continue to push about 1/4 of a foot per day into the ground. There are estimates that, we're going to be storing, a lot of water. If you just assumed 200,000 acres, nice round number, at 1/4 a day, right? 1/4 foot per day for 5 or 6 months here, or as long as the water keeps flowing out. They're projecting that the water will continue to flow out of the reservoirs, or out of the reservoirs and the mountains here all the way into the fall. So we're looking at storing a lot of water. Yeah, it's going to be good. I don't know the exact number because, again, I'm not 100% sure on how many acres are actually doing it, but it's a lot. And then I got another question: how long this water available to mitigate drought in California? I guess how long will this water maybe be available? So yeah, it not only from the reservoirs, we're going to have a lot of water that, again, probably 3 or 4 years, but the recharging of the groundwater is going to help get us a long way too. I'm actually kind of interested and fascinated about the SGMA deal, right? The Sustainable Groundwater Management Act. I have a feeling that, they look at averages, and this particular year is just going to throw a big wrench into how much water is potentially available, to growers and so forth. So the GSAs, the groundwater sustainability agencies, they're going to have kind of an interesting dilemma, I guess, of figuring out what is a sustainable yield for a basin now that all of a sudden the basin, like the Tulare Lake Basin, got that much water coming in. So it's going to be kind of an interesting topic. But yeah, so sorry I'm not answering your questions with like pointed answers. It's just because nobody really knows, right? They keep projecting how much water is going to be coming out of the mountains, and it seems to continually to be more than they project. So as long as we can keep groundwater basins recharging and people continue to put groundwater basins online, it's going to be a lot of good news for a lot of for California. Let's put it that way. All right, so let's see if I can. So yeah, the dams are spilling still. We've got all these reservoirs are filled. This is Lake Oroville here. You may recall that in 2017, this dam had a crack in it, and as they were spilling it for the first time in its history, actually, that crack turned into a big hole, and water was just spilling off the side here, going down into the Feather River. And there's some pretty cool YouTube videos and stuff if you want to take a look at those. But they just kept cutting away and cutting away. Well, they had to keep releasing because they didn't really have any other options, and so they started to worry about the security of the dam and so forth. And luckily, some break from the weather that particular year allowed them to stop spilling and inspect damage. And then, it was like $1 billion or whatever to get the new slip and slide there fixed for emergency spill. And luckily we did it, because this particular year, 19, I think it actually used it again, and now in 23, it's spilling again. So reservoirs are full, as you saw, at least the ones on the west side, or the east side, of the San Joaquin Valley and Sacramento Valley, and they're spilling. So it's good. Everything's good, but we got to utilize that water as much as we can, right, for groundwater recharge, and that's what everybody's doing. The water's inexpensive right now, and with credit systems, you get credits for doing groundwater recharge. Everybody's trying to capitalize on that as much as they can going into the future. So okay, not to leave out the lower Colorado River system. The Colorado River, just to give you an idea, actually, if you guys want to scan that QR code with your phone, you're welcome to. It takes you to a website that has a pretty good visual of all of the reservoirs data graphically, kind of shows you what's going on. And if you click on that page and you scroll all the way to the bottom, you can also look at reservoir data for like Lake Mead, Lake Powell, Lake Havasu, all of the lakes along the Colorado River system. And so this is the discharge from Lake Powell. They had sent down I think it was like 1.8 million gallons per minute down the river down into Lake Mead to try to do some cleaning up of certain sections of the river. Sediment settles in certain areas, and it kind of narrows the river and so forth. And so they saw this opportunity with all of the snow happened in Colorado and so forth, or in the Colorado system, that that they could do a little bit of cleaning of the river. So they were releasing quite a bit of water down this river, peaking that flow rate, trying to improve the channel flow conditions and so forth for future operations. But their projections are that, you know, the river will, the Lake Powell and Lake Mead, which are the two largest on that river system, will still be well below average, actually, this particular year. But they're saying that they're climbing about a foot a day. Each of the reservoirs is climbing in elevation about a foot a day. They're going to go up probably 70 or 80 feet. Again, people are making projections. How accurate they are, I don't know. I'm just repeating what I've read. But saying 70 or 80 feet is what we're going to gain in both of these reservoirs, which will still only put us at like 30% capacity or something on the reservoirs. So Colorado River system still actually needs a lot more rain and snow. So in theory, if that El Nino pattern does show up, maybe the Colorado River system will benefit from this too. This really only impacts like Metropolitan Water District. They get some of their water from the Colorado River system, and then the Imperial Valley, which I know some of you probably have some citrus down in the Imperial Valley. So so I didn't want to completely leave that out, because I knew you guys do some farming of citrus down there. All right, and then just my last slide on the water update, I guess, is I just wanted to kind of show you this because I found this fascinating. You know, when you look at this, there have been, you know, over the, you know, from 800, you know, all the way down to where we are at today. You know, there have been some mega droughts in that time frame. And so, I mean, you're talking, what is that, from 850-ish to 1050-ish? You're talking about 200 years of drought, right? Where it's drier years than wetter years. And, you know, what we've seen here kind of in our lifespans is kind of wetter years. And then we get a little bit of a drought pattern going here into 22, man, and we're all freaking out thinking the world's going to end and stuff, you know. And could you imagine if, you know, if one of these 200-year droughts happened to start now? I don't want to put that juju on anybody, right? We don't want to see that happen here, but that can happen in California. You know, so it is quite possible that you know, moving into the future, we do have more drought years than we have wet years. Although over the last, whatever that is, you know, 500 years or so, that has not been the case. But so keep that in mind, keep that in the back of your head as you know, we go through 5 years of drought and then we get a bunch of rain. It's like, okay, it's not as bad as it could be. All right, so now I'd like to transition here into the topics of distribution uniformity and efficiency. These are two topics that in the irrigation industry we talk about often, and often they get mixed up or interchanged. People think distribution uniformity, or DU, is efficiency, or efficiency is distribution uniformity, or they think they're the same thing. And I want to kind of clear up any misconceptions that there might be out there. Okay. And some of you probably know some of this stuff, and if you do, I'll at the end here, I'll kind of hit some of the highlights that you should be looking for in your citrus fields. Okay. So let's start with distribution uniformity, or DU. So I'll be calling it DU a lot, just so we're aware of what I'm talking about here. This is a measure of how evenly we apply water to the field. All right. So that's kind of a key piece there. It's how evenly we're applying it. Right. We could apply it evenly and applying way too much, or we could be applying it evenly and not applying enough. Right. And so this doesn't tell us anything about how well we're using the water we're applying. It's just, are we applying it uniformly or not? Right. And uniformity is, in my opinion, it's the bigger thing that you should be paying attention to on farm. Efficiency, and I'll talk about that too a little bit more, but efficiency is a little more difficult to pinpoint and to understand and to talk about. Distribution uniformity is way easier to understand, to measure, to see, to fix, efficiency is a little more of an art. Distribution uniformity is a little bit more of a science. Okay, and I'll explain what I mean by that as we move through here. One of the things I'd like to point out too is that the efficiency is always a percentage, whereas distribution uniformity is always a decimal value, and that was not always the case. The industry, the irrigation industry, 15 or 20 years ago decided that we can't talk about distribution uniformity as a percentage anymore because people are already confusing efficiency and distribution uniformity. And now what we have them both as labeled as percentages, people are always going to be confused. And so the industry changed to the fact that we were going to have, DU always be a decimal value. So with that said, you will still come across stuff, where DU it says DU and it's listed as a percentage, and that's some legacy stuff that hasn't been moved, hasn't been removed, I guess. But we should be talking about distribution uniformity as like it's 0.92 or it's 0.77 or whatever it is, and not as a percent. So that way we all know we're all talking about the same thing, which is distribution uniformity. And of course, that means that a DU of 1.0 would be perfect, meaning every single spot in the field received the same amount of water. That's nearly impossible to achieve, and I can explain why at the end. Okay, but most of our systems that we have, especially our permanent systems that we do on citrus, will have distribution uniformities of around 0.9. That is totally achievable. All right. So this is just a graphic or an illustration kind of distribution uniformity. And what you'll see here is that, we obviously have a spot in the field on the top graphic there, or the top part, that is not getting enough water, right? Ultimately, we would want this part of the field to get that much water, and we're not getting it. Well, what's happening is we did actually apply the correct depth on average, right? If you look at the average that we applied the correct depth. The problem though is that the water that we need here that should have been applied here was actually applied over here. And so we needed to improve the distribution uniformity. We need to bring that water and actually have it applied over here. And so this is a design issue or maintenance issue. And so one of the things we want to do is we want to make sure that, our systems, when they're performing or when they're on, they are applying the water as uniformly as possible. And it starts with a good design and it ends with proper maintenance, right? And so you have to continually maintain a good design to keep that uniformity. And so this is what we want ultimately, right? We want the amount of water that we've got to be evenly applied to all spots in the field. And of course, it's never going to be perfect, but it's going to be, we can get close to perfect. Okay. And one of the things I'd like to point out here is that there are classes that are available on this through Cal Poly and the ITRC. This is where I worked before I came to Laurel, and I used to teach the distribution uniformity classes. And so usually middle of June, it actually just wrapped up last week. They teach a class on how to do distribution uniformity. It's a week-long class, and you can get the program from them. They'll walk you through the program, everything that you would need in order to do a uniformity test on your farm. If you don't have the time or the resources to send somebody to a class like that, there are mobile labs, typically through the NRCS or the RCD, which is the Resource Conservancy Districts, your local ones, that will do some uniformity testing for you. Laurel has actually started to make it a practice to do uniformity testing for customers to help diagnose problems and so forth that you're having in a field. And so, we'd probably be even willing to come out and do some uniformity testing for you if you needed it. Okay. So, but you kind of have to start with a good DU. If you don't have a good distribution uniformity, it's hard to, it's hard to really be efficient or effective at anything else in terms of irrigation applications or fertilizer applications for that matter. Those of you that are doing fertigation or chemigation, where you're injecting fertilizers or pesticides, chemicals, herbicides, whatever it is with your irrigation water, that only gets applied as uniformly as the water gets applied. So if your uniformity looks like this top chart here, where you have some stress that's going on in some of your plants, those plants are going to be stressed because of water and because of nutrients, because your water is not taking those nutrients to those plants. So those of you that are doing fertigation, you absolutely have to make sure that your distribution uniformity is high, because otherwise you're not getting the full benefit of your fertigation system. So why worry about a good DU? I've kind of touched that just a little bit here, but it does make irrigation scheduling easier as well. So those of you that are, scheduling is answering two questions: when and how much. If you can answer those two questions, right, then you're doing a good job with your irrigation scheduling. The real question though on the how much part is, how long do I have to run my system? Okay. And going back to actually this slide here, right? If you're to think about this, right? If you're trying to ensure that these plants get enough water, what is your, sorry, I got to turn my annotation back on again here. If you're trying to ensure that the plants are getting enough water, right, at this particular location here, what do you have to do everywhere else, right? Well, in order to get that much water there, you basically have to irrigate more water here. So basically thing's going to just kind of copy what you have there. But to get this spot, the driest spot, the right amount of water, you have to have a whole lot more deep percolation in the wet, or in the either the perfect spot or the wettest spot. And so that means you have to run it longer. And so to determine the amount of water that you have to apply, you have to know what your distribution uniformity is. And so the higher your distribution uniformity is, the easier scheduling is, because basically the amount of water that the plant used is the amount of water that you have to apply. When you have poor uniformity out there in the field, you have to now, figure out, okay, well, how much more extra water do I have to apply to meet that particular water requirement? Okay. Increased efficiency as well. So now, linking this back to efficiency, the difference between DU and efficiency, right? We talked about DU being how evenly you apply the water. Well, efficiency is how effective you are with the water. Well, the more uniform your application of water is, the more effective you're going to be with the water. And so, and of course, assuming that you have good scheduling, and I'll talk about that in just a minute here, but that's kind of the idea. You want to make sure that you start with a good distribution uniformity, and then you can get to a good efficiency. Okay. The other benefits that this has is the increase in the representative sampling locations. And when I'm talking about the sampling locations, I'm referring to the fact that you have soil moisture sensors. A lot of you're doing probably leaf balms. Some of you're probably doing maybe sap flow. You might be looking at the size of fruit, all of the different things that you're looking at out there in the field. When you have a high distribution uniformity, the differences between maybe the size of your fruit or the stress in the plant leaf or whatever you're measuring again, those level out. And that's what we want. We want the entire field to be basically the same. So that way your quality is the same everywhere and so forth. So having a good distribution uniformity really helps kind of level all those things out. And I'll show you an example with some sensor reliability. I had a project where I improved the distribution uniformity, and it also improved my accuracy of my sensors. And so just looking at this real quick, this is it, right? I had a field and it had a distribution uniformity of 0.73. And so if you look at that there, if you look at the 0.73, that's the pink line. So I had some, and I made this all relative depths. So I had some locations in the field that were getting basically 2.5 times as much water as the average. And I had some spots in the field that were getting 60% of the average. And then if you kind of said, okay, well, if you look at plus or minus 10%, let's say, right, of average, about what percentage of the field is within plus or minus 10% of the average. And 0.73 doesn't sound like a terrible distribution uniformity, and it's not, right? But the problem is that it's not good either, by the way. But the problem is that only about 36% of my field was within plus or minus 10% of the average. So if I'm placing a soil moisture sensor out there, or if I'm going to do a leaf bomb or sample fruit or whatever the case might be, I have essentially a 36% chance that I'm looking at a quote unquote average spot or average location. So if I put a soil moisture sensor over here at this spot, it's going to tell me never to water. And if I put a soil moisture sensor over here at this spot, it's going to tell me always water, right? And I have basically a 36% chance of finding a range here that is basically giving me kind of what's happening on a majority of the field. Whereas if I increase that distribution uniformity to a 0.89, we swapped out some parts and made some improvements to the system, and we got it up to 0.89, which is, again, I was saying 0.9 is typically pretty achievable. We now all of a sudden have, if you look at this line here, right, we now only have some sensors or some locations that are getting 1.5 times. We have some locations, or I should say a location, that is getting 80% of the water, but now about 71% of my field is getting water that is within plus or minus 10% of the average. So now when I put soil moisture sensors in the field, much higher chance that I'm going to find a quote unquote representative location, much higher chance that the fruit I'm going to go sample is representative of what I'm going to see at other locations in the field, right? And so distribution uniformity does play a big role in those kinds of things. I got a couple other questions here. DU seems like a static situation case, but how do you account for disruptions such as planting on slope that never ending attack on? Yeah, no doubt. Yeah, so basically you run into problems, right? And one of the issues that you run into is unequal drainage, and I'll actually cover that here towards the end. Okay. Would you want unequal distribution if the active root zones for themselves are not uniform, for instance, with trees? I'm not 100% sure I understand that question. If the active root zones are themselves not uniform, meaning you have a different root ball in one area and a smaller root ball in another area, I think might be the question. I'll come back to that one too. Okay. Good questions. All right, let's keep rolling here. Computer doesn't like controlling it remotely, I guess, here, but okay. So just to give you an idea how it's calculated, we look at the average of the lowest quarter divided by the average infiltrated over the entire field. This is the calculation for DU, and the average lowest. So like, for example, if you had 100 acres, right, the lowest quarter would be a quarter of 100 is 25. And so you'd be looking at the 25 acres that's receiving the least amount of water. You would take the average of that, and then you would compare that to the average applied to the entire field. Okay. And so that seems kind of, like, well, how do you know where the lowest quarter is and so forth? Well, the program that was developed at ITRC basically tells you which locations to go to, where to take pressure measurements, all the stuff that you would need in order to kind of determine what the lowest quarter is in the field. If you were to kind of look at it in terms of, all these buckets here, I think those are actually blueberries, but this is kind of another way of looking at it. If you were to think about it this way, if every single one of those, buckets was on a scale and we were applying water, right, we could individually weigh every single one of those buckets, and then we would know what the average weight is. And then we would also know what the, the lowest weight is of the lowest quarter. So if we had 1,000 buckets out there, we'd say, okay, 250 buckets is the lowest quarter. Which of those 250 buckets weighs the least? Average all those and compare that to the total. Okay. The question about unequal drainage kind of ties into this a little bit. This is grown in a substrate, so it's artificial soil, which means it has like 0 holding capacity. So they have to basically put on the exact amount of water when the tree or bush in this particular case needs it. You have to make sure that you turn on that irrigation system, that the water doesn't drain to the bucket at the lowest point, right? And so we now have technology, the manufacturers have technology that allows us to have what's called a CNL emitter, a closed non-leak emitter. So when the pressure gets below, I think most of them are set at 10 feet, which is about 4 PSI, 4.3 PSI. the emitter will actually shut down and it will stop water from emitting until the pressure goes above 10 feet. And then that emitter will start emitting again. So to prevent some of the non-uniformity that you might get because of slope, which I believe one of the questions was kind of alluding to there a little bit, we can design some of that in. Now, a coyote chewing on it or a gopher chewing on it, right? Those are going to cause non-uniformity. That's a problem. And so those are things that we'll just have to fix, but we can design around some of the issues like slope. Okay, efficiency is basically it's a calculation that estimates the amount of water that was beneficially used compared to the amount of water that was applied, right? And so remember, uniformity is about how evenly we apply the water. Efficiency is about how much of the water we applied was actually consumed by the plant. The target, how much of it went to the target, okay? And so this is, always expressed as a percentage, 100% being perfect. And then we also have this problem with it's hard to achieve, or it's hard to understand what the efficiency is because, well, how much of it actually got used by the plant? And this is why I was saying it's difficult and, and it's an estimate really, because we don't really know. We have ways of figuring it out, but it's still, kind of like, I'm pretty sure that's right kind of thing, that how much of the water actually got consumed by the plant as opposed to how much of it went to depercolation or runoff and so forth. It's an estimate, okay? And so you can see here, this would be an efficient irrigation event. Sorry, I always forget to turn my pen back on, but the top graphic there is an efficient irrigation event, where the bottom one is not efficient, although the uniformity in both cases is actually very high. We applied the water uniformly in both cases, but in the bottom case, we just let it run for too long. Right. And so, yeah, we did have a high uniformity, but we also had a poor efficiency because we applied twice as much water as we needed. And so in that particular case, the efficiency is likely 50% because half of the water did not go to the target or the plant. Right. So efficiency is very different than uniformity. Uniformity, again, measures how evenly you apply it. And uniformity also kind of indicates or does not indicate that if we applied the correct amount of water. Efficiency does tell us if we applied the correct amount of water, right? Because it's comparing what was applied versus what was used. Uniformity just tells us how evenly, okay? But again, determining that beneficial use is the challenging part because, what is a beneficial use? I got a slide on that, but what is a beneficial use, right? Crop ET is the biggest beneficial use. There are others. And making estimates of what was beneficial versus what wasn't is really, again, where the art part of it comes in. And again, efficiency can only be determined after the fact, right? You only know how efficient your car was as you drove to Las Vegas to go, to that bachelor party or whatever, when you get there and you put more fuel in your car and you can calculate how many miles per gallon you got, right? You can make an estimate of what you think you're going to get on your way there, but you only ever know how efficient you really were after the fact. And that's kind of a problem. Whereas with distribution uniformity, if it's designed to maintain properly, you know how it's going to perform every time. You're going to have a DU of a certain value. We do have two efficiency terms: irrigation efficiency, application efficiency. I would argue that a lot of times people are referring to application efficiency when they're actually talking about irrigation efficiency and vice versa. In the end, it doesn't really matter, though, in this particular case. It's not like mixing up DU and efficiency. Typically, the difference, though, is application efficiency is to a single field, and it's one single event. So how well did I do on my last irrigation event, right, for this field? Whereas irrigation efficiency can be a much bigger basin, like how well is an irrigation district doing? How well is an entire ranch or farm doing? And how well did they do over the course of a year rather than just looking at a single event? But in the end, it's basically the same calculation: how much water was beneficially used versus how much was applied. Okay, and so there's your equation, right? And then the beneficial uses, of course, crop ET, big one. Salt leaching is another one. Climate control, maybe you need to do some cooling in certain times of the year, maybe even frost protection certain times of the year. Cultural practices is another one. Do you have a cover crop or not? That would be considered a beneficial use as well. Are you trying to water in fertilizer Maybe the plant doesn't necessarily need it, but you got to get the fertilizer in the ground. That would be a beneficial use. There's lots of different caveats to the idea of a beneficial use. Okay, and of course we want to have a high efficiency because number one, water quality degradation, meaning we don't want to be leaching our fertilizers down into the groundwater. So if we can have a high uniformity and a high efficiency, all of those fertilizers go where they're supposed to go. With that said too, that means we don't have to pump as much. We don't have to apply as much fertilizer. The size of reservoirs and pumps can be smaller because we don't have to apply as much water. Drainage problems go away because you don't have the water sitting there pooling on the surface and so forth. You don't have to buy as much water. And then on top of that, you're spending all this money on extra, and then on top of that, your yield goes down because the crop is stressed because certain areas aren't getting enough, certain areas are getting too much. You're not getting your fertilizer spread around. So you want to have a high distribution uniformity and a high efficiency. And that's really what this last little slide here is about, is combining these two, right? Apply the water uniformly as you can, put on the correct depth, which will give you a good efficiency, minimize your losses, your deep percolation and surface losses. If you do all those things, you'll have a good event. Yeah, so the last thing is these are some things that you want to look for when you're if you're trying to evaluate how well your system's doing, right? So these are the components of non-uniformity for systems, right? So if I can get my slide to transition real quickly, one note about uniformity on, say, citrus, right, is we're not trying to irrigate the entire area. We're only worried about that each tree gets the same amount of water. We're not worried about the area out there in the road getting water because we're not really growing anything out there. So in this particular case, it's not like a forage crop or something where you're trying to make sure that we're evenly applying water to the entire surface area. We're trying to evenly apply water to each tree, right? So that's kind of a consideration to think about. And if you were to look at this, like what's the wetted area here, right? This is one of our account managers here doing an evaluation of a drip system, determining pressures and so forth. But what's the wetted area there, right? If you compare this, maybe it's about 50% of the area is actually wetted, right? And that's probably about all you need, maybe 50-60% for trees to be productive. Okay, so here are the factors. These are the kind of the bottom lines here that you need to be looking at, right? There's 4 of them, and they're on the left column there, and then so there are components, 4 components, and then there's some factors that affect each. So the 4 things that you need to be looking for in your fields, if you're kind of wanting to get an idea of what's going on, are pressure differences. You're not going to ever have it, but you want to have basically the same pressure everywhere if possible, right? Because of friction, elevation changes and stuff, you're not going to. But now, because of things like pressure compensating emitters and micro sprinklers and so forth, we can kind of compensate for those pressure differences. But ultimately, you want to have as uniform of pressures across your field as possible. Okay. You want to make sure that you don't have flow variations between your emitters because of things other than pressure, and that's why it's called DU other there. We don't want we don't want things like plugging, wear, root intrusion, back siphonage. You're always going to have some non-uniformity though, because the manufacturers can't make the products exactly the same all the time. So the CV, the coefficient of variation, is going to change because they manufacture 24/7. Well, the temperature outside changes, the humidity changes, all those things affect the product, that plastic piece that they're making. So you're always going to have some non-uniformity due to flow differences, even though you're at the exact same pressure. And we want to kind of figure out what those are. And then unequal drainage, we talked a little bit about, when you're pulsing that irrigation, you're on for 30 minutes and off for 2 hours and on for 30 minutes and off for 2 hours. If you're on a slope, and you're not managing that unequal drainage from those emitters at the bottom of the hill will never shut off. Right. And so that plant at the bottom of the hill is always getting water, where the plant at the top is getting it per your schedule. So you want to make sure that you have, maybe CNL emitters in that case. And then the last thing is unequal spacing of plants or emitters. And probably in most of your guys' conditions, you're not going to have this issue because you're planting the trees on the same spacing and you're putting so many emitters or so many micro sprayers per per tree. And so since the spacing is the same, the emitters are the same, you're not going to have any non-uniformity. But if you add on a block or something, right, and you change the spacing of that block, and you keep the same number of micro sprinklers per tree on the new block, but the block has changed tree spacing, now all of a sudden you have some non-uniformity between what your original block and your new block. So keep that in mind too. Try to keep things standardized out there in the field. Okay, and then this is my last slide here. I've done a lot of evaluations over the years with students when I was teaching at Cal Poly, and you can see the two big factors there are DU other, meaning flow variations other than pressure, like plugging and wear, and then pressure differences. Those, most of you are probably in micros, I guess, on your citrus. Some of you aren't, but those of you that are, you can see that pressure variations, especially if you're using, say, like a Bow Smith emitter that has no pressure regulation function. It's just simply an emitter or a micro sprinkler that can cause some big differences in flows out there. So you want to have good designs on those, trying to maintain the same uniformity everywhere. Okay. And then there's my contact information. If you guys, you can scan that QR code as well. It'll give you all my contact information. If you want to reach out, if you want Laurel to potentially come, bid a project for you or do a distribution uniformity evaluation. If you just want to have a conversation with me about something that's on your mind, of course, about irrigation, I'm happy to do that. Okay.
And I would like to thank Dr. Gaudi for sharing this information with us today, and to all of our participants for joining the Citrus Research Board for today's webinar. We appreciate everyone who tuned into this year's webinar series. Like I said, all of the talks have been recorded, and the first 3 are now available on our website. So please visit citrusresearch.org to view those. And to stay up to date with upcoming CRB events, please visit our website. And we appreciate your attendance today, and we hope to see you again at a future CRB event.